Hello, everyone. My name is Niloy Biswas. I'm a graduate student doing a PhD in statistics at Harvard. Today, I'll be speaking about estimating convergence of Markov chains using couplings. This is based on a paper which is joint work with Pierre Jacob and Paul Vanetti. First of all, I will give some motivation behind why assessing convergence of Markov chain Monte Carlo is an important question. Secondly, I will talk about couplings of Markov chains, and in particular, L-Lag couplings to diagnose convergence. And thirdly, I will give some applications of our methods in a range of Markov chain Monte Carlo algorithms. So the motivation for this problem is something familiar to many of us, I hope. We have a target distribution of interest, pi, and we wish to generate samples from this distribution pi. Example applications here include calculating integrals that are otherwise intractable. Secondly, Bayesian inference. So in the case of Bayesian inference, our target distribution pi corresponds to the posterior, and we may want to estimate quantities such as the posterior mean or form credible intervals from our posterior. Now, given this target distribution pi, how can we sample from this? Markov chain Monte Carlo, or MCMC, are one of the most common and successful methods to address this question in the past few decades. For MCMC, we have an initial distribution, pi naught, which we use to start our chain. So we sample from pi naught to get the value of the chain at x naught. And then from every time t1 onwards, we sample xt based on a fixed kernel and the previous value of the Markov chain, which is denoted by xt minus 1. Now we choose our kernel k to be pi invariant, such that as this chain xt runs for an infinitely long number of time steps, the distribution of this chain converges weakly to the target distribution of interest, pi. Now, this is an asymptotic result under some regularity conditions. In practice, we must stop our Markov chain at some finite time, capital T. The question we ask is, how close is the distribution of the chain at capital T, which I denote by pi t, to the target distribution, pi, which the chain attains only at infinity. Now, for practitioners, this is of recurring concern because every single algorithm you run, that's MCMC, is stopped at finite time t. And it's very important to know whether we are running our Markov chain for a long enough number of time steps, or conversely, we are running it for too long and we're wasting precious computational resources. So this motivates the main reasons we started looking into this project. Now, to give a very stylized and simple example of a Markov chain Monte Carlo algorithm, imagine our target distribution of interest is a standard normal distribution on the real line. We consider a Markov chain initialized at exactly the point 10. And here we're using a random walk metropolis Hastings MCMC algorithm. You can see for this one trajectory of our Markov chain, the chain reaches around 0 around time 50 onwards and stays in that region. Now, just looking at this one trajectory, one may say that this chain seems to have reached close to stationarity from time 50 onwards. We can also look at multiple independent trajectories to see what the general trend is, which is what we do next. So this plot now is formed by simulating multiple independent trajectories from time 0 to 150. And then for each time t, I have multiple points coming from my independent trajectories, which I then use to form this histogram at each time. So you can see at time 0, I have a peaked histogram about 10 because all my chains are starting exactly at 10. And now we can see from perhaps time 100 onwards, the distribution of my Markov chain from time t100 onwards seems to be like a Gaussian, a standard Gaussian. And we know this because we know how to visualize this one-dimensional standard Gaussian. That is our stylized target in this example. So for this question in blue, for this simple chain, we could say, based on this one-dimensional example, just by looking at trace plots, time 100 onwards is sufficient for burn-in. Now, I'm going to give a more precise answer to this question, which is the topic of the paper I'm going to present. So we answer this question in blue using couplings of Markov chains. The paper I'm referring to here is called Estimating Convergence of Markov Chains with L-Lag Couplings and has been published. So first of all, I'm going to introduce a notion of distance between probability distributions. I'm going to focus on this talk on total variation distance. We also consider one Wasserstein distance in the paper. Now, total variation distance can be defined through a supremum over some test functions, h, where these test functions are bounded between -1 and 1. And inside the supremum, we have absolute value of difference between the two expectations, where one expectation is taken with respect to my distribution pi t, and the other expectation is taken with respect to my distribution pi, which the chain only reaches at infinity. Now, as practitioners who might be doing Bayesian inference, say, total variation distance between the distribution of my chain at time t and my target distribution pi is a very useful quantity to know. For example, it captures errors we might get from histograms and credible intervals. What I mean by this is if my TV between the distribution pi t and pi is less than epsilon, then the histograms I form using my Markov chain run up until time t, and I look at the points from time t, are epsilon away from the true histogram coming from the true posterior. And a similar statement can be said about the credible intervals. So total variation distance is a practically useful quantity that we wish to know more about and that we wish to get upper bounds on for our Markov chain Monte Carlo methods. And this will be the focus of this talk. So to summarize the end result before going into some of the details, on the left-hand side of this figure, you can see the histograms at different points in time that I'd shown previously. And you can see from this stylized example, it seems like 100 onwards is sufficient. Now, on the right-hand side, I have 3 lines. The solid line corresponds to the true total variation distance. And as is consistent with the histogram plot, you can see from roughly time 100 onwards, my total variation distance is very close to 0. For the dashed lines, these correspond to upper bounds of the true total variation distance, where these upper bounds are formed using our coupling-based methodology. You can see there are 2 dashed lines corresponding to different values of the lag L, which I'll explain shortly. And in particular, the greater the L, so for example here, L being 150, the tighter the upper bound on the true total variation distance. So here, choosing a larger L ensures that the upper bounds we get remain informative, even for smaller time steps. Now I'm going to explain how we get these bounds. Before I do so, I want to emphasize that in this stylized example, we are able to very accurately estimate the true total variation distance. We are able to very easily just plot the one-dimensional trace plot And we're also able to visualize the true target distribution pi by construction, because it's a distribution we know and because it's one-dimensional. When we move into higher dimensional examples and more sophisticated distributions such as posteriors, then such visualization is not always practical. And also estimating the true total variation distance is not always feasible. So these bounds apply to those settings too, and that's what I'll cover soon. Now, before I go into applications, we need to highlight how we generate our upper bounds. Our upper bounds are based on L-Lag couplings, which I define in this page. L-Lag couplings correspond to a pair of Markov chains, xt, yt, which evolved jointly such that marginally the distribution of xt is the same as the distribution of yt for each time t, and this distribution I denote as pi t, such that xt and yt converge in distribution to our target distribution pi of interest. So marginally, they are just the same as our original Markov chain of interest. However, they are not necessarily independent and they depend on each other. In particular, xt and yt minus L, so I've introduced a lag here corresponding to capital L, meet exactly at time tau, where tau is a random time. And tau is given by the smallest time period such that xt exactly equals yt minus L. A natural question looking at this definition of tau is that whether such tau can actually be finite in continuous state spaces, and whether we can actually get two high-dimensional chains to exactly meet in continuous state spaces. The answer is it can be done. A lot of it is based on the recent work done, for example, in the unbiased MCMC with couplings paper. But even further back, there is work by Val and Johnson looking into things called maximal couplings. And there is an entire literature dedicated to these kind of questions. So simulating such tau can be done. And I'm giving you one simple example in this figure now. Again, I'm focusing on the stylized example that I had shown before, which is I initially start my chain xt at the value 10, and I run a random walk Metropolis Hastings. You can see up to time 150, it runs like the original Markov chain, marginally. At time 150, where 150 here corresponds to my lag, capital L, I also start the second chain, yt. And from time 150 onwards, I evolve the two chains jointly, such that eventually they meet at a random time point, as shown here to be 190. So in this case, my lag L is 150 and my tau is 190. So details which give the exact algorithms to run such simulations are all in the paper and in the related literature recently on coupled MCMC. Now that we know how to simulate such tau, I'm going to highlight a simple upper bound of the total variation distance in terms of these meeting times tau, which is given in the equation of the bottom of this page. On the left-hand side of this equation, you can see the total variation distance between pi t and pi. On the right-hand side, you can see an upper bound where the only random quantity in our expectation is this quantity tau. So to estimate this expectation on the right-hand side, I simulate coupled chains independently multiple times to get different values of tau. And I simply look at the average of this quantity inside the expectation to estimate this upper bound. Note that I only need to simulate tau a fixed number of times to get an upper bound which holds for all t. So these are functional upper bounds. And this is exactly how I generate the plot shown on the right-hand side of this figure. And you can see we have different parameters L in the upper bound, and the larger the L, the tighter the upper bound. However, the larger the L, also the longer the running time of the algorithm. So this gives us a simple example highlighting our methodology. Now, I'm going to discuss briefly existing convergence diagnostics before going into more sophisticated applications. So this question of how close is the distribution of the chain at time t to the target distribution at infinity has been extremely well studied. I'm just highlighting an incomplete list here. So there are analytical results in applied probability, both from 2 decades ago to things which are published very recently. In these analytic results, bounds are often of the form of an unknown constant c, which depend on the initial distribution, times some decaying function ft. For example, ft might be exponentially decaying with respect to t. Now, such bounds are analytically very informative because sometimes they will analytically capture the effect of dimension, the convexity of the target distribution, and many other features. However, this constant at the front is unknown. Therefore, for practitioners for a fixed time t, these bounds are not empirically informative. On the empirical technique side, there are papers, so I highlight 2, where Cowles and Rosenthal try to estimate some of these constants. And also Johnson actually used couplings, proposing an idea closely related to what I've just described to also come up with upper bound to total variation distance. And outside of this, there are more popular convergence-based diagnostics, such as the R-hat, which do not directly measure total variation distance. I should also note there is a recent R-hat paper which discusses some of the limitations and proposes new things too. Okay, so now giving you some more sophisticated examples for our methods. First of all, I highlight the Ising model and show 2 different Markov chains. Firstly, I consider single site Gibbs targeting this Ising model. And also I consider parallel tempering. And you can see the upper bounds we produce using couplings on the figure below. Now, something interesting is highlighted here. First of all, looking at the line which is dashed corresponding to single site Gibbs, you can see in the first 1,000 iterations, where each iteration corresponds to a full sweep, you can see single site Gibbs appears to have a faster decreasing upper bound compared to parallel tempering. Yet from around time 1000 onwards, there is a plateauing of this upper bound. What's happening here is that this target distribution is bimodal, that the density is bimodal. In particular, if you switch signs of all the states, the probability density function equals the same value. So for this first decrease in this single site Gibbs example, this corresponds to the single site Gibbs chain mixing very well in one of the modes and then slowing down as it struggles to find the second mode. In comparison, parallel tempering does not have this plateauing because it manages to explore both the modes well. So this kind of captures the bimodal distribution that affects single site Gibbs samplers for this Ising model. Second example is related to Bayesian Logistic Regression. And I focus in particular on Hamiltonian Monte Carlo with different parameters. So I use a credit data set where I have 1,000 observations and roughly 50 dimension. We have a Gaussian prior, and we have our logistic regression likelihood. We wish to target the posterior using HMC with different parameters, epsilon and capital S, corresponding to the length of the steps and the number of steps in HMC. And also I have a parameter-free polygamma sampler for the same posterior. You can see a few things on the plot below. First thing to highlight is that the polygamma sampler converges to stationarity much more quickly based on our upper bounds, as shown by the line going most quickly to 0 corresponding to the polygamma sampler. Secondly, for a fixed epsilon, I consider a different number of steps for the leapfrog in my HMC. And you can see our upper bounds are also informative about which number of steps might be the best to choose in terms of fastest burn-in bias. A technical note to highlight here is that these bounds are all upper bounds, so the true total variation ordering may be different. However, these are still informative nonetheless as practitioners. Now, I'm going to highlight another extension, which is, so far I've talked about a stylized example and something related to the Ising model and something related to Bayesian logistic regression. Now, the question I'm going to ask is, can such diagnostics work in even larger scale settings? So this points to another paper I've worked on. This is based on this is called coupling-based convergence assessment of some Gibbs samplers for high-dimensional Bayesian regression with shrinkage price. This is a recent paper available on arXiv. To summarize some of the takeaways from this paper, we focus on Bayesian linear regression and Gibbs samplers for posteriors from Bayesian linear regression. And even in such challenging settings where you have 2,000 observations and nearly 100,000 dimensions, we can use L-Lag couplings to diagnose convergence in less than 1,000 steps. So this paper is a vindication of both Markov chain Monte Carlo working in such high dimensional settings, but also highlights that couplings are effective in such high dimensional practical Bayesian computation settings. And some useful references, the code for both the L-Lag couplings paper and the most recent page I just showed, corresponding to coupled half-T prior for Bayesian linear regression, are both available online. And I've also included some references to related work and related lecture notes related to couplings. Thank you.